Hey, what's up, guys? Happy Tuesday, asynchronous day. Here I am sitting here. I'm just doing the homework right now, which isn't due till tomorrow, just some area and volume mixed practice homework. I'm getting the answer key all ready for you. I'm going to go through it quickly so you can't see. Getting the answer key all ready for you because I'm going to send it your way after you turn it in so you can check your answers. That's how we're doing things here as we're rounding out the year. So hopefully you have fun with these problems at least here, just knowing that you're going to get the answers anyway. You can check them, but you should also ask questions. Okay, ask questions. Don't just wait for the answer key. Ask me questions, please. Okay, so I'm doing this, and here I noticed that I've actually put in this methods and meaning box into your homework, and then I realized that you haven't put this on your toolkits yet. You haven't put the volume of a sphere formula in, and we know what a sphere is because we defined that in chapter 7, so I'm not too worried about that. But the volume of a sphere, that should go in your toolkit, so you might as well organize it. You saw it kind of briefly introduced Monday's class, and you watched the video for homework, that 3-minute video at the end of the Desmos. So hopefully you know what that formula is, but let's put it into our toolkits so that we have it in one safe place. And then also, too, we haven't put in the volume of a pyramid formula or the volume of a cone, right? Volume of a cone formula. That's not in your toolkit. It's easier. So let's put those in here. And then also another thing you'll need to know for the homework, because I did the homework, went down. I was like, we haven't talked about this yet. Check it out. Surface area. Surface area of a sphere. Okay, so that's another important one here. I'll talk about where the heck this surface area formula comes from a bit, or at least one way we can remember what it is here a little bit later. Okay, so let's commit this stuff. The stuff we did in Monday's class. Stay organized. There's a boatload of information as you owe in a class like geometry or an upper level math. So part of the challenge you're getting this year is how do I organize this information? How do I use it to my advantage? How do I break it out tactically is what I meant to see. How do I break out some information? And where do I keep it so that I can pull upon it if I need to use it? Okay, so one place could be a toolkit, for instance, where you keep your formulas. Pyramid formula, we saw this one in class today. Of course, pyramid here. If I have a pyramid and I have the same base area as another shape, same height as another shape, and that shape being a prism is what I'm getting at here. Prism's volume, base area times by height. How many of those pyramids volumes could fit into that? Prism's volume, well, 3, right? 3 as we saw the other day. So in order to get, right, the volume of a pyramid, okay, of course it's going to work the same way, except the cross sections are different, right? Cross sections are different for pyramids than they are for prisms. Remember, all cross sections are congruent of a prism, okay? Cross section. So I got a base, and this is my base. This one's a hexagon, and I drew a hexagon here. Nice. My cross sections of this hexagon are congruent to the bases. Look, I have this regular hexagon looks regular to me, and if I move it inward a little bit here, and I'm going along the edge of this, if I cut out a section that's perpendicular or parallel, cut out a section, I run a plane through this parallel to one of the bases, the intersection with the solid gonna be congruent to that hexagon which is at the end here. So that means that all my cross sections going from one base to the other base are congruent. That means my volume is just simply that base area times by, fill it on up, times by the height. And pyramids are a little bit different, right? Pyramids, because our cross sections get sequentially smaller until we get to that vertex, and then cross-section, the area is nothing at that one point because a point has no area, right? A point has no area. A point is infinitely small in space. So anyways, our cross-sections for at least this square pyramid are all going to be squares, but they're all going to be sequentially smaller squares as we get closer and closer to the vertex. So anyways, we have less volume, and what we saw through observation, we're not proving it this year, is that the volume for pyramid, and let's do this in black so I some sort of logic with how I lay out this into the toolkit here, because I'm running all the volumes in black. Volume equals V equals, well, it was just a third of what would fill up a container that would have an identical base but be a prism instead, right? Two prisms here. So we just find whatever the corresponding prism's volume is, base area times by height, and then we got to divide by 3 so we can fit 3 of those pyramids in there. And that's just going to be true, right? If we have a polygonal base and it's everything that connects to a single point, 1/3 of the size. Then if we have a polygonal base and everything connects to an identical base on the other side. And that's pretty neat, right? That's pretty neat. That's pretty neat that it works so elegantly. 1-to-3 ratio. Freaking sweet here. Cones are the same way, okay? Cones are the same way, except, right, like we can talk about the base area, right? I do a hexagon for this one because it's true for every pyramid here, right? Base area, okay? Height, I forgot to sort of label the attributes here, Okay, base area times by height, but we don't, like over here, there's no volume. Over here, there's no volume, right? So this is 2/3 of the volume outside of that, of the prism. Anyways, and then a third here. Anyways, we're not going through the proof this year, so you don't have to worry about the logic. But why this works out, it just does. We can observe it too, okay? Cones are base, right? Circular cones, okay? We'll get to, just come up with the formula for a circular cone. Okay, again, cones bases could be circular, or they could be oblong, or they could be like elliptical. They could be an oval. You know, it's kind of the same thing as ellipse. But anyways, as long as they're curved, right? Curved planar figure connecting to one point that's off the plane would basically be the definition to a cone. But if that figure is a circle and not just any like curved figure, then it would be a circular cone. And now we can actually come up with a more sophisticated formula because we know the base area. Okay, we know through Cavalieri's principle that the cylinder that would contain, that would have the same radius, okay, and the same, draw the height in here, okay? So notice here, this isn't a right cone. This isn't a right cone. This is something different than a right cone. Right cone is, we go from the vertex, we draw the perpendicular, and we hit the center of the circle. We're a little bit off here. But anyways, there's my H, okay? So I have my height, I have my radius, as I marked down there, radius here, and I know that this cone, because we saw through observation, we could prove it, but we're not proving this here. Trying to save some time wherever we can. It would take 3 of these guys to fill in a corresponding cylinder that had the same radius. It just had 2 circular bases and everything else in between. Okay, so a cone doesn't fill nearly as much as its cylindrical corresponding shape here. It fills up 1/3 of it, okay? So we'd have here about 1/3 of the volume of a cylinder would be in this cone, and then on the outside here, within that cylinder, the other remaining 2/3. All right, so anyways, we have V equals 1/3, and since this is R, right, same thing, right? We take the area of the base here, but we can actually come up with it because it's circular, so pi r squared h. There we go. We got a second formula for us today, the volume of a circular cone. Make sure it's in your toolkit so you can have it. You can pull this formula up whenever you need it over the next few days here, and hopefully into the future. That'd be nice here too. Rounding things out with sphere. Spheres where I thought the lesson got really interesting yesterday is like, okay, it's not just observation anymore. It's not just sort of like guessing how many of these could fit into a cylinder or how many of these could fit into a corresponding prism. It was actually, they proved something mathematically to you. If we were right about this, and we are, we could prove it, but we're not going to. We just saw it through observation. And if we were right about this observation that it's in a 1-to-3 ratio with a corresponding cylinder, we should be able to use these formulas actually to get us to the sphere. Again, through observation, we saw this, that we take a cone. So notice here, I'm just going to sort of go through the same logic of that video that you saw yesterday. So we can get to the volume formula of a sphere. Okay, but the idea, what they wanted to show you was that a sphere's volume is equivalent to the sum of 2 cones, right? The sum of 2 cones' volumes, that these cones have the same height as the sphere, and they have the same radius as the sphere, okay? If we take this and we take this, and you should have seen it, we watched it, we observed it, we take this. So if I had this, I could have actually maybe showed this to you right now. I could have done it right now. I could have gotten all wet, it could have been all messy. One of these cones here, if I fill this up with water and poured it into this hemisphere, it would fit perfectly. It would actually fit perfectly. So that means that if I have 2 of these guys, pour it into this, pour it into another one, its brother, which is lost now because my daughter lost it. But anyways, I can put them together and this would be entirely filled with water, okay? So I'm not gonna redo that experiment that you observed yesterday, but I will talk about that 3-minute video that sort of talked about where this volume of the sphere formula comes from, because really it comes from this plus this. Okay, what do we notice here? Okay, so the sphere, and if I had it, you kind of see it here. Okay, this sphere here has the same height. Okay, if I had both of them, would have the same height as the cone, and it has the same radius. So a sphere, we usually don't talk about the height of the sphere, right? We talk about just the radius. That's the defining thing about a sphere, is the distance from the center in space from the actual ball itself, from the actual sphere itself. And that would be the radius, right? That equal distance would be referred to as radius here. So here, I want to come up with the formula for spheres that has just to do with radius. So if I have two cones that have the same height as the radius, I will talk about the height of these cones, okay? And we need height because, look, height is in the formula for the volume of a cone, right? We have 1/3 pi r squared h, right? H here, okay? But as you saw in the video yesterday, I can replace h with 2r in this formula because, well, these radii are all congruent right here. And I told you it had the same height as this sphere. And what's the height of this sphere? Well, the height of the sphere is equal to 1 diameter of the sphere, which somebody in each class said, ooh, that's a diameter right there. Its height is the diameter. And what's another way we can write the diameter? A diameter equals how many radiuses? 2 radiuses added together. So this is r, and this is r. Okay, so here, the height of this sphere is 2r. So we're comparing this to what you saw yesterday, is that the height of this cone could also be expressed in terms of the radius. Okay, the radius here, and the radius will be 2r, radius 2r here. Okay, so anyways, mathematically, algebraically, right, if we accept that we can pour 2 of these cones into the sphere, as we saw, and it worked perfectly. It looked wonderful there, okay? If we accept that we can do that, we can simply add the 1/3 pi r squared plus h plus 1/3 pi r squared h together to become the volume of the sphere, okay? Volume of the sphere, so we can generate a formula for the volume of the sphere here, okay? Am I ready to add these together? Well, no, because I told you that, remember, through our observations, those cones had the same height as the sphere here. Okay, so we can actually eliminate one of our variables here because the cones had the same height as the sphere. So what would that height be? It would be 2r. It would be equal to the diameter of that sphere here. So I'm going to replace that, and that just makes it easier for me to combine this in a more elegant way and write a formula that has fewer variables in it. And we just need to worry about the radius of the sphere, which is what we usually care about when it comes to the sphere, is what the radius is here. Okay, so I'm going to replace h with 2r. Look, the height of this is 2r, and I'm going to replace h here with 2r, and I'm going to simplify this until I've reached the agreed upon, set upon volume of a sphere, which you can see if you Google, if you get a standardized test later, they're going to say, hey, here's the volume of the sphere, practice. Because a lot of these formulas, they just give them to you on standardized tests. They don't expect you to memorize them. Come on in here. Or maybe your teacher, maybe distance learning, and we didn't get to some of these formulas here. They don't want to hold it against you, okay? So I want to simplify this here, but it's nice to see where it came from. That actually does come from somewhere. It's not just this magic gobbledygook that we have here, okay? So now I have r squared. What do? R squared times by 2r. Remember, numbers multiply together, so I might move the 2 over here. 2 times 1/3, and then I have r times by r squared. Well, that's r cubed. That's nice. We want to get r cubed because volume is a cubic calculation, right? Volume is 3 dimensions. Keep that in mind for how you keep this formula here. Okay, I'm going to move the 2 to the front. Remember, if I'm multiplying stuff here, so look at this here. I'm just using something called the commutative property, which is here I'm multiplying 1/3 times pi times r squared times 2 times r. And when you're multiplying a whole bunch of things, order doesn't matter. So you can rearrange the things that are being multiplied together to make it more simple, more elegant for you to work with. And I want to put the 2 in front of the 1/3 because I'm going to do that next. I'm going to multiply them together later. Okay, so now I have this 2 times by 1/3. Okay, and then I have pi r cubed. Very good. Is the volume of the sphere, and I'm going to get there just like they showed you in that 3-minute video. This is much longer than a 3-minute video. This is with somebody you know rather than some random guy who made it. It's a really good video. That was a good video here. So let's go ahead and figure this out here. Okay, so I'm going to combine these here. So 2 times 1/3, well, that's just 2/3. Okay, 2 times by 1/3, well, that's just 2/3. So now I got this here. Now I have 2/3 pi r cubed plus 2/3 pi r cubed. Okay, how many pi r cubes do I have in total? Okay, I got 2/3 pi r cubes right here. And I got 2/3 pi r cubes right there. How many pi r cubes in total do I have? Well, I got 2/3 of them. I'm adding another 2/3 together. Well, then, 2/3, add another 2/3. 2/3 plus 2/3 is 4/3, right? Because when you add fractions, you have to just add the numerators. Denominators don't change. Okay, so I have 4/3. okay? I have 4/3 pi r cubed, And there it is, the volume of a sphere formula. Yeah, proved it, or not proved it, but we justified it a bit. If we accept that we can add those two cones, which through observation, yeah, we can. We can do that. Sometimes we can do things inductively when we don't have time to prove them deductively. And sometimes it's just nice to know that their deductive proof is out there. So we'll just observe and take it from there, okay? Volume is this for a sphere. Volume equals 4/3 pi r cubed, okay? The thing about volume to remember, using the volume formula here, is the number 3 appears twice. Number 3 appears twice. One, it's a volume. We know it's a volume calculation because volume is a three-dimensional calculation because it's length, width, and depth, right? That's how many square units we would want to fit into a sphere. So r cubed makes sense, right? That we have this whole cubing thing here, okay? The reason why I'm making a big deal of this is I'm going to tell you now rather quickly the surface area formula for spheres, okay? I'm not going to bother with pyramids and cones. Let's not bother with that this year. Normally I would, right? Normally I'd have a lesson. And actually, the surface area of a cone, ooh, that's pretty tricky, okay? So I'm not even going to touch that this year. Pyramid, you can figure out the surface area, right? Because these are all triangles on the lateral faces, and the base is just some sort of polygon. We know how to get areas of polygons here. Anyways, surface areas of spheres, okay? Gonna follow a formula, okay? Check this out. It's pretty neat. The proof is kind of complicated. Here, you want to watch 17 minutes? This is pretty good. 17 minutes of this here. You can watch. There's a great YouTube channel called 3 Blue, 1 Brown. And if I go to this, it probably has like, I don't know, I'm going to guess like about 3 million views. That's my guess here. It explains where the formula for the surface area of a sphere comes from. And I'm just clicking through to see the views because I get so jealous. You know me. There it is, 4 million views. I'm in the wrong business. I need to work on my game a lot. Work on my game and improving my videos. Because this video compared to 3 blue, 3 brown, 1 blue, 3 blue, 1 brown, that's it here, is way better than my videos. We can all agree on that here. But anyways, they got over 4 million views in that. Man, that's good money. Anyways, I'm in the wrong business. I gotta make my videos better anyways. But anyways, they filmed this. You probably heard it. I mean, generally in most classes, like, oh, cool. Like I've watched those videos. There's generally a couple people have watched the 3 blue, 1 brown videos. But anyways, I like what they did here because the surface area of a sphere is actually equal to, and this is kind of coincidental, it's equal to surface area equals 4 times the area of the great circle. The area of the great circle of that sphere. The great circle of that sphere. So 4 pi r squared. 4 times by pi r squared here. Okay, and then what they did here is what I like about this here. The name of the channel, is 3 blue, 1 brown. They made 4 circles because that's 4 pi r squared. And they made 1 brown and 3 blue. Or 3 blue, 1 brown. I like what they did there. Anyways, look at it here. Just look at this diagram real quick here. And you're just going to have to accept it kind of because I'm not going through the proof. It's a 17-minute video. I'm not going to watch it here. But it does come up on your problem set. This formula here. 4 pi r squared. Just 4 times. 4 times the area of a circle. Okay, 4 times the area. So check it out here. I got a hemisphere right here. I have this. I just ripped this out. I didn't even cut it. That's how savage I am at the end of the year here. So I'm cutting corners. Okay, cutting corners. All right, man. Get a little bit of this off here. I got a little bit of edge, not so good here. Okay? All right. Been stuck in this room for what? 6 months? I don't know. I did move halfway through the year. But anyways, this is the great circle. Okay, I see some people's names there. Look, it's clearly just scratch paper. On that side, oh, I got scratch on the work on that side. Anyways, this is the great circle, and this is a hemisphere here. So this here, the area of this is what? Pi r squared. Don't even have a pen, but the area of this is pi r squared, right? Have the same radius as the sphere. How many of these hemispheres does this circle cover? Okay, let's look at it here. Does it cover that much of this hemisphere? Okay, well, it seems like it covers a little over half if I look at it this way, okay? But wait a second, a lot of it's open here. Okay, a lot of it's open here. Okay, it turns out that if I had cut this thing up, and placed it and arranged it really cleverly, this circle here, okay, this circle here would cover exactly half of this hemisphere, meaning that this circle here, pi r squared, I'd have to have 2 of these pi r squareds thing to cover the surface of this hemisphere here. Okay, so what does it mean for an entire sphere? Well, I take that circle, I can only cover, let's see, I put it right there. That's only about a quarter of the sphere. It is a quarter of the sphere here, okay? So the formula for the surface area of a sphere is just 4 times the area of the great circle of the sphere. And that's just the circle of the sphere. And that's just a neat thing, right? A neat connection here is that, you know, the area of the great circle, hey, you need 4 times of that to cover the whole thing, to paint the whole thing, to wrap the whole thing up. And anyways, the proof of that is actually in your textbook. It's a little challenge section here, but I think you really need to take Algebra 2 first to really understand the proof that surface area is 4 pi r squared, okay? So let's wrap this one up here, because one of the things that are confusing for people is this. The number 4 appears in both the surface area formula and the volume formula for spheres. So these are easily mix-upable, right? Mix-upable formulas here. Volume formula of a sphere is 4/3 pi r cubed. Surface area of a sphere is 4 pi r squared, okay? Some ways to keep them sort of separate in your minds, well, go to the 3's, okay? I have a 3 in the denominator here. That means I'm going to have 3 as an exponent. Okay, no justification other than I'm just trying to point out to you things that are common. I have a 3 in the denominator here. I have a 3 in the exponent. That's the volume formula, okay? Because volume is a 3-dimensional calculation. So r cubed, that's the one that goes with volume. 4/3, that's going to be my coefficient, okay? Because I have 2 3's in the volume formula. Here, there's no 3, so my coefficient is just going to be 4, right? I'm not going to divide by 3, right, if I'm doing problems like this here, okay? So just one tip for keeping those 2 formulas in mind. 4/3 pi r cubed versus 4 pi r squared for the surface area, okay? Best of luck on your problem set today. Message me any questions if you have them. Don't wait for the answers. Just send questions your way. I'd love to answer them here. Take care, guys. Bye.